In this problem class, we're going to look at double integration. So we're going to cover the topics reversing the order of integration. We're going to cover polar coordinates, calculating volumes and areas, and also calculating center of mass. So I'm going to cover some problems that do this, but of course I'm not going to get through them all. So I'll let you work through those yourself and look at the online solutions. Let's start with problem 1. So in this problem, we're looking for the integral from 0 to 1 of So as usual in these problems, we have to calculate the region of integration. So that's our first step here. So let's draw our x and y coordinates. Remind ourselves what the actual integral is. So we have the integral from 0 to 1, integral from square root of x to 1 of the square root of 1 plus y to the power of 3. And we're given the order of integration. It's dy dx. So that means that our first integral is the y integral, and our second integral is the x integral. So what we're going to do first of all is write down what the limits of integration are by just reading them off our integral. So the limits of integration for the inner integral, that's the first integral with respect to y, is y going from the square root of x to y going to 1. And our outer integral, x, has limits 0 to 1. So you see that we can interpret that as the region enclosed by the following curves. Y is equal to the square root of x, which we can rewrite as x is equal to y squared. We've got y is equal to 1, x is equal to 0, and x is equal to 1. So let's sketch that on the xy axis. So here's my y-axis, and here's my x-axis. Let's start off by sketching the line y is equal to the square root of x. So that's going to start at the origin and move off like that. That's our line y is equal to the square root of x. We also have got y is equal to 1, which is a horizontal line passing through y is equal to 1. And we've got the lines x is equal to 0 and x is equal to 1. Those are vertical lines. X is equal to 0 and x is equal to 1. We want to find out where the point of intersection is, and you can see that that's going to be at the point 1, 1 and 0, 0. Now you can see that there's one region of integration here. There's one region that's completely enclosed by those bounds. But even if we didn't see that, we could still figure out which region it is by sort of unpacking the instructions that we have from the limits of integration. So let's take a look at those again. We're told that for x, pick a value of x between 0 and 1. So let's sketch that. Here's my value of x between 0 and 1. And for that value of x, take a value of y between the square root of x and 1. So we can take our little tracer up to the point here. Y is equal to the square root of x. And then we're going to go all the way up to y is equal to 1. Y is equal to 1. So you can see that the region of integration then is the upper left-hand space there. Let's sketch that. Let me just indicate that by green. That's our region of integration. Let's call that omega. And our next step now is to figure out how to reverse the order of integration. So we're going to instead take our outer integral over y and our inner integral over x. So we can do that from our region of integration. What we're going to do is we're going to pick a value of y between 0 and 1. And for that value of y, we're going to take x values between 0 and x is equal to y squared. That, of course, is the same as this curve here, just rewritten as x as a function of y. So by reversing the order of integration, our new limits of integration will be y between 0 and 1 and x between 0 and y squared. So now we can set up our integral with the order reversed. So our integral will be, integrand doesn't change, of course, so we have 1 plus y cubed, that stays there. I'm reversing the order, so the x integral is going to be done first, followed by the y integral. And I've got to match up my limits of integration. So the inner limits of integration correspond to the x integral, so that goes from 0 to y squared. And the outer limits of integration correspond to the y integral, so that's going to go from 0 to 1. Alright, so now we're ready to do this integral. We see that the first integral, the x integral, doesn't actually have any x's in the integrand here, right? So when I do that integral, I'm just going to have my integrand multiplied by x, because I'm treating y like a constant. Multiplied by x, and we're going to evaluate it at the limits 0 to y squared dy. So let's substitute in x is equal to 0 and y squared. X is equal to y squared gives me the integral from 0 to 1 square root of 1 plus y cubed y squared dy. So we're going to solve this by substitution, and our substitution variable is going to be the thing inside the square root sign there. It's going to be 1 plus y cubed. So let's set u equals to 1 plus y cubed, which implies that du is equal to 3y squared dy. So u at 0 is going to be equals to 1. U at 1 will be equals to 1 plus 1 is 2. And I can substitute in now those expressions. So I've got the integral from 1 to 2 of u to the power of 1/2, square root of u, times y squared dy, which is 1/3 du. So I can take that 1/3 out the front. So we can do that integral. It becomes 1/3 u to the power of 3 over 2 divided by 3 over 2 from 1 to 2. So we get the integral of 1/3 times 2/3 times 1 to the 3 over 2. Sorry, 2 to the 3 over 2 minus 1 to the 3 over 2. So we get 2 over 9 times 2 to the 3 over 2 is 2 root 2 minus 1. So that's our solution for question 1. Now the rest of the questions on this side of the sheet, questions 1 through 5, you'll notice that they're all pretty much similar. Calculate a double integral by first of all sketching the region of integration and then reversing the order of integration. So it's good practice for you. I'll let you try those yourselves. Let's move to question 6, which is a polar coordinate question. So we've got an integral we need to calculate by first changing to polar coordinates. So looking at question 6. The integral we're interested in this time is the integral from square root of 2 divided by 2 to 1. Integral from 0 to the square root of 1 minus x squared times dy dx. So you notice here that the integrand is actually just the number 1. So we're going to be calculating an area here. So let's take a look at these limits of integration and try and work out from this what the corresponding region of integration is. So the outer integral we notice is x going from the square root of 2 over 2 to 1. And y going from 0 to the square root of 1 minus x squared. So if we interpret these in terms of curves, we see that we have the curve x is equal to root 2 over 2 is 1 over root 2. We've got x is equal to 1. We've got y is equal to 0. And we've got the line y is equal to the square root of 1 minus x squared. Now what does that last one represent? Well, let's square both sides and rewrite it by bringing that x squared over to the left-hand side. So I get x squared plus y squared is equal to 1. So you see that this is the unit circle centered at the origin. So let's sketch these 4 different curves and see what region is bounded by them. Okay, so let's sketch the xy plane. Here's my y-axis. Here's my x-axis. We're going to sketch the curves corresponding to x is equal to 1 over root 2, x is equal to 1, so let's sketch those. Here's x is equal to 1. Here's x is equal to 1 over root 2. We've also got y is equal to 0, that's just the x-axis. And I've got the unit circle, so I'll just draw the upper right-hand quadrant of the unit circle. And we can see where the intersection points are. So this is the point x is equal to 1, y is equal to 0. This is the point 1 over the square root of 2, 1 over the square root of 2. Let's draw in what these lines were. So this was x is equal to 1 over root 2. We've got x is equal to 1. We've got our curve, our unit circle, x squared plus y squared is equal to 1. And we've got y is equal to 0. Now, how did I come up with those intersection points? Well, I'm looking for the intersection of my unit circle with the curve y is equal to 0. So I can just substitute in y equals to 0 into the unit circle, which gives me x squared is equal to 1, which implies x is equal to plus or minus 1. So there's going to be 1 on either side of the x-axis, but this is obviously the one at x is equal to 1, y is equal to 0. Likewise, where is the intersection point of my line x is equal to 1 over root 2 and my circle x squared plus y squared is equal to 1? So let's substitute in x is equal to 1 over root 2 into my unit circle, so that gives me x squared plus y squared is equal to 1, which gives me y squared is equals to a half. So y is equal to plus or minus 1 over root 2. And again, this is obviously the side on the positive y-axis. So we have the point 1 over root 2, 1 over root 2. So you can see that there's one region that's bounded by all of those curves, but again, if we didn't see that, we could figure it out by looking at the limits of integration. So they're telling us, take a value of x between the square root of 2, 1 over the square root of 2 and 1. So pick a value of x somewhere over here between 1 over root 2 and 1. And for that value of x, integrate from y is equal to 0 to y is equal to the square root of 1 minus x squared, which corresponds to our circle. So integrate over this line here. So you can see that the region of integration then is going to be the shaded region here. So that's our omega. Okay, so what we're going to do now is we're going to convert this into polar coordinates, because as you can see, there's clearly a circular symmetry here, a rotational symmetry. So let's see what that would look like. Our polar coordinates are r and theta. So there's theta, and r is the distance along that radial line. We need to write down what our limits of integration are. So in polar coordinates, you can see that theta is going to be going from 0 to pi over 4. So you can see that theta is varying between 0 along the x-axis to 45 degrees, which is this line here. So that's the point 1 over root 2, 1 over root 2. Now what about r? Well, you see that r is going to start at this point, which is on the line x is equal to 1 over root 2, and end at this point, which is the unit circle. So the second of those is fairly straightforward. But we need to figure out what's the correct form for that first limit of integration. So it's going from the line corresponding to x is equal to 1 over root 2 and ending at the point x squared plus y squared is equal to 1. So r is equal to 1. So let's think about how we can express the line x is equal to 1 over root 2 in polar coordinates. So again, remember that polar coordinates x is equal to r cosine of theta, and that's equals to 1 over the square root of 2. So what I'm going to do is I'm going to rewrite that now as an expression for r as a function of theta. So r is equal to 1 over the root of 2 times cosine of theta. So that's going to be my first limit of integration. R is equal to 1 over the square root of 2 cosine theta. And my second limit of integration is going to be 1 because I'm ending at the unit circle. Okay, so let's rewrite my integral. So I've got the integral. My integrand was just 1 because I'm calculating an area here. I'm replacing dy dx with r dr d theta, not forgetting that extra factor of r. And my limits of integration are going to go from r is my inner integral, so 1 over the square root of 2 cosine of theta to 1. And theta goes from 0 to pi over 4. So my first integral is with respect to r. I'm going to get r squared over 2. Subbing in the limits, r is equal to 1 over the square root of 2 cosine of theta, and r is equal to 1. So that's going to give me integral from 0 to pi over 4. I'm going to get, let's take out that factor of a half, and then I'm left with 1 squared minus 1 over root 2 cosine theta squared. So that's 1 over 2 cosine squared theta d theta. Okay, so there's a number of different ways that you could try and do this integral. I'm going to use a standard integral. So if I take out 1/2, split this up into 2, 0 to pi over 4, of 1 times d theta, minus, let's take out that factor of 2. So I'm just splitting up my integral into two different pieces. So I've got 1/2 of theta from 0 to pi over 4 minus 1/4. And what's the integral of 1 over cosine squared theta? Well, that's one of the tabled integrals. It's the tan. So we've got the tan of theta from 0 to pi over 4. Okay. So that gives us 1/2 of theta over 4, which is pi, 1/2 of pi over 4, which is pi over 8, minus 1/4 of, so tan at pi over 4 is 1, and tan at 0 is 0. So I get pi over 8 minus 1/4. And so that's the area of the shape enclosed within this region of integration. So in that case, we used polar coordinates to make our integral a lot simpler. We were actually asked in the question to do that. We'll see in some of the other problems that we actually just want to use polar coordinates because it's a bit more convenient. Before we do that, let's take a look at a volume question. Let's take a look at question 7. And I'm only going to do the first part of this. So in question 7, we're asked to calculate the volume of this solid. And we're going to describe the shape of the solid. So let's take a look at that question. Question 7. And write down what the integral is we're solving. We're calculating the volume. Integral from 0 to 1, integral from 0 to 1 minus x of 4 minus x minus 2y dy dx. Now, we want to evaluate this integral and then try and interpret what we're actually doing here. So let's sketch our region of integration by writing down what the limits of integration are. So we have the outer integral is x, and x is varying between 0 and 1. The inner integral is y, and y is varying between 0 and 1 minus x. So we can put those together and get a series of lines. We've got x is equal to 0, x is equal to 1, y is equal to 0, y is equal to 1 minus x. So we can sketch those in the xy plane. Here's y, here's x. So we've got the line x is equal to 0, corresponds to the y-axis. We've got x is equal to 1. I've got y is equal to 0, corresponding to the x-axis, and I've got the line y is equal to 1 minus x. So that's a line with a slope of minus 1 passing through the point y is equal to 1, x is equal to 0. And you can see that the points of intersection here, straightforward to calculate these. This point here will be the point x is equal to 0, y is equal to 1. This is the point 0, 0. And this is the point x is equal to 1, y is equal to 0. And again, you can get those by just substituting in the appropriate values into y is equal to 1 minus x. So you can see here that clearly the triangle here is our region of integration. So we're going to pick a value of x between 0 and 1. And for that value of x, we're going to integrate between y is equal to 0 and y is equal to 1 minus x. So this is our region of integration. Okay, so let's do our integration now. We can jump right into it. We're not asked to modify our integral. So we've got the integral from 0 to 1, integral from 0 to 1 minus x of 4 minus x minus 2y dy dx. So what's that going to become? We do our y integral first. So we have 4y minus xy minus y squared. Limits of integration are 0 to 1 minus x. Let's substitute in y is equal to 1 minus x and y is equal to 0. So we have 4 times 1 minus x times 1 minus x minus 1 minus x all squared. You can see that we're going to have to do a little bit of multiplying out here in the hopes that things will simplify a bit. Integral from 0 to 1. 4 minus 4x minus x plus x squared minus 1 plus 2x minus x squared. So we're going to get a little bit of cancellation here. X squareds cancel out. So I'm left with integral from 0 to 1 of 4 minus 1 is 3, minus 4x minus x plus 2x, that's going to be plus 3x dx. So that will be equals to 3x plus 3x squared over 2, 0 to 1. So that will be equals to 3 plus 3 over 2, which is equal to 9 over 2. Oh, I think I got a little minus sign wrong here, so that was a minus sign there, minus sign there, minus sign there. So I've got 3 minus 3 over 2, which is 3 over 2. That's better. Okay, so now we're asked to calculate or to figure out what exactly the shape is that we've just calculated the volume to be 3 over 2. So let's take a look again at our integral. And we see here that we've got the integral over a region of integration, some function dy dx. But remember that a volume integral is described as follows. It's the integral over a region of integration omega of a function f of x and y dA, where dA could be dx dy or dy dx or whatever, and we interpret that as being the volume below the surface z is equal to f of x and y. And in this case, f of x and y was equals to 4 minus x minus 2y. So I can rewrite that as x plus 2y plus z equals to 4, which we recognize as a plane. It's linear in x, y, and z. So what we can interpret this volume as is the volume under the plane x plus 2y plus z equals to 4. Enclosed by the curves x is equal to 0, x is equal to 1, y is equal to 0, and y is equal to 1 minus x. So we can explain it like that. And if you're feeling arty, you can try and draw a picture of that, but I'm not able to do that. Okay, let's finish up with a question involving center of mass coordinates. So I'm going to move to question 9. Let's take a look at that. In question 9, we're asked to sketch a lamina, a flat shape, bounded by these curves. We're given a density and we want to calculate the coordinates of the center of mass of the lamina. So this is question 9. So let's write down what the bounding curves are for the lamina. We're told it's bounded by y is equal to 2 root x, y is equal to 2, x is equal to 0, and x is equal to 1. And we're also told that the density of this thing is x times y. So our first step, as always, is to try and sketch what this thing looks like in the xy plane. By drawing all of those curves on there. Okay. So we've got x is equal to 0. Oops. So we've got x is equal to 0. X is equal to 1. Y is equal to 2 root x. It's going to look something like this. And y is equal to 2. So this is the curve x is equal to 0, x is equal to 1. We've got y is equal to 2 root x, and we've got y is equal to 2. And let's find out where those points of intersection are. So where does the line y is equal to 2 and the line y is equal to 2 root x meet? So we have y is equal to 2 is equal to 2 root x. You can see that that will meet at root x is equal to 1, or x is equal to 1. So the intersection point there is x is equal to 1, y is equal to 2. We also have this point here. X is equal to 0, y is equal to 2. And we have the point x is equal to 0, y is equal to 0. And you can see that there's only one region that's bounded by those curves. It's this region here. So that's our region of integration. So now we're going to calculate the center of mass coordinates of our lamina. And we're going to do that using these formulas. So we have the center of mass coordinate in x is going to be given by 1 divided by the total mass times the double integral of omega x delta xy dA. And we've got the y coordinate is equal to 1 over m double integral y delta xy dA. So the first thing we're going to need to do is to calculate the mass itself. So let's remind ourselves what that is. It's going to be the double integral of the density over the area. So we've got three double integrals to do here. So the first one, the mass, is going to be equals to the integral of our density, x, y, and we need to decide what our limits of integration are. So let's go have a look again at our region of integration. What we can do here is, let's say, pick a value of x. We have a certain amount of freedom here, so I'm going to pick a value of x between 0 and 1. And for that value of x, pick values of y between y is equal to 2 root x to y is equal to 2. So our limits of integration will be pick a value of y between x between 0 and 1, and for that value of x, pick a value of y between 2 root x and y is equal to 2. And we're going to do the y integral first, followed by the x integral. Now you can think about how this would change if you were to do the integration the other way around. Again, we have that freedom in this particular question. So we've got the integral from 0 to 1. And I'm doing the y integral, so I've got x y squared over 2, subbing in y is equal to 2 root x to y is equal to 2 dx. So that's going to give me integral from 0 to 1, subbing in those values of y. I've got x times 2 squared divided by 2 minus x times 2 root x squared divided by 2 dx. So I'm going to get 2x minus 2x squared dx, which will give me x squared minus 2x cubed over 3 when I carry out that integral from 0 to 1. So I'll have 1 minus 2/3. It'll be equals to 1/3. So our mass is equal to 1/3. The next integral that we need to do is the integral of x times delta xy dA. So again, I'm going to use the same region of integration, so the same limits of integration apply. All that's changed here is my integrand, so it's x times the density. And I'm going to do the y integral followed by the x integral. So that's going to give me equals to 0 to 1. Carrying out that y integral first, so I get x squared y squared over 2 from y is equal to 2 root x to 1. That will give me, subbing in there, y is equal to 2 root 1 and 2 root x. So I'm going to get x squared that's a 2. X squared times 2 squared over 2 minus x squared times 2 root x squared over 2. So I get the integral from 0 to 1 of 2x squared minus 2x cubed dx, so it looks very much like the integral we just did, So when I do that, I'm going to get 2x cubed over 3 minus 2x to the power of 4 over 4 from 0 to 1. So that's going to be equals to 2/3 minus 2 over 4, or 2/3 minus a half. So that'll be equals to 4 minus 3 over 6 will be equal to a sixth. So that's the second of our integrals. We can use this now to calculate the center of mass coordinate in the x direction, because it's going to be given by 1 over m times the double integral of x times the density. So in other words, it's going to be, our mass was 1/3, so it's going to be 1 over 1/3 times 1/6, which is equal to 3 over 6, which is equal to a half. Now, to calculate the y center of mass coordinate, we might be tempted to just appeal to symmetry, right? And just sort of say, well, this thing looks pretty symmetric about the xy. The density is kind of symmetric. It's equal to xy. But in fact, if we look at our region of integration here, you see that I can't swap x and y to get the same shape here. X and y are not symmetric in the region of integration. And to use symmetry, I need to have two symmetries. I need to have symmetry in my density. In other words, when I swap x and y, I get the same density. That's true. But I also need symmetry in my region of integration. So if I swap x and y here, if I take sort of the mirror image, I don't get the same region of integration. So this is not going to have symmetric center of mass coordinates. I need to do the integral itself. So let's take a look at that. I've got the double integral over omega of y times delta xy dA, which will be equals to, again, using the same limits of integration. That doesn't change. What does change is our integrand. And I'm going to do the y integral followed by the x integral. So I get the integral from 0 to 1 of x times y cubed divided by 3 to root x to 2. Let's substitute in y is equal to 2 and y is equal to 2 root x. So I get x over 3 times 2 cubed minus x over 3 times 2 root x cubed. So tidying that up a little bit, we're going to get 8x over 3 minus, well, we've got 8 over 3 x times x to the 3 over 2. So that would be x to the power of 5 over 2. Or I've used x times x root x cubed is x times x to the 3 over 2, which is x to the 5 over 2. So we get the integral, it becomes 8 over 3 x squared over 2 minus 8 over 3 x to the power of 7 over 2 divided by 7 over 2 from 0 to 1. So that's going to become 8 over 3 is 1 over 2 minus 8 over 3 Hello? Hi, Brendan. Good, good. Can I call you back in like 5 minutes? Okay, bye. So doing that integral, we get 8 over 3 x squared over 2 minus 8 over 3 x to the power of 7 over 2 divided by 7 over 2 from 0 to 1. So that's equals to 8 over 3 times 1/2 minus 8 over 3 times 2 over 7, which will become 4 over 3 minus 16 over 21, which is equal to 28 over 21 minus 16 over 21, which is equal to 12 over 21. And if I divide out a factor of 3 on top and bottom, I'll get 4 over 7. Okay, so we need to calculate the y-coordinate of the center of mass, so that's going to be 1 over m times the integral I just calculated. So once again, m was a third, so 1 over m is 1 over 1/3 times 4 over 7, which will be 12 over 7. So our center of mass coordinates then are going to be equals to, just looking back up again, we found 1/2 and 12 over 7.